Clauses 4, 5, and 6.1 of the ISO 9001 standard map the operational context and build the quality management system primarily as a mechanism for risk prevention. The structural outcome of Clause 6.1 operates as a defensive perimeter, defining the exact actions necessary to protect an organization from operational failure. But possessing a highly engineered defensive method has limited utility if the organization lacks explicitly defined forward-looking targets. That requirement is addressed by Clause 6.2. This diagram maps the transition. The defensive network of 6.1 forms the baseline, but it only functions when a structured grid of explicit targets locks into it, represented by Clause 6.2. Quality objectives serve as functional system requirements, replacing static executive demands. True quality objectives are dynamic, measurable targets that require deep systemic integration to function correctly. When management implements these objectives incorrectly, the result is mechanical pressure. The system extracts effort through employee burnout rather than expanding its operational capability. Avoiding that burnout requires a rigorous architectural framework of cascading metrics. It also relies on continuous, bidirectional feedback loops between executive leadership and the factory floor. Clause 6.2 is the exact mechanism that takes a theoretical risk prevention model and transforms it into a measurable, adaptable operational engine. Strategic goals are abstract by nature. To be effective, they have to cascade downward, translating from a high-level vision into specific directives at the individual operator level. This 3D architecture shows how that alignment works within the QMS. Strategy at the top layer relies on the balanced scorecard, which drives departmental KPIs in the middle, flowing down to individual OKRs at the base. Treating this cascade as a strictly linear, top-down mandate is a structural failure. Operational reality dictates what is actually possible. Feedback vectors regarding feasibility have to flow upward from the OKR base level, pushing back against the downward strategy vectors. Establishing functional targets requires this iterative, bidirectional loop, constantly calibrating executive direction against ground-level capability. Once that alignment is set, we have to examine the anatomy of the metrics themselves. Continuous improvement requires precise measurement. You cannot improve what you cannot accurately quantify. The standard baseline for designing these metrics relies on the traditional SMART framework: specific, measurable, achievable, relevant, and time-bound. Modern QMS implementation requires expanding this acronym to SMARTer, aggressively integrating two additional functions: evaluate and report. Executing the evaluate function in real time, such as immediately analyzing and recognizing a specific first quarter win, acts as a critical psychological driver for maintaining system momentum. A bidirectional cascade ensures targets are grounded in operational reality, while SMARTer evaluation provides the timely feedback staff need to see the immediate impact of their work. This structural alignment allows individuals to track their own path to success, reducing the reliance on forced compliance. The most common operational failure in implementing Clause 6.2 occurs when an organization misunderstands the achievability constraint of its targets. Consider a standard scenario. An executive mandate dictates a flat 10% reduction in manufacturing errors for the upcoming year. Look at this split-screen model. The left side demonstrates the incorrect approach, applying mechanical pressure. Management demands better results without altering the underlying operational system. This static system forces the operator to absorb the objective through pure effort. The inevitable outcome of this method is psychological exhaustion and employee burnout by year's end, yielding zero resilient quality improvements. Now look at the right side of the model. The exact same 10% reduction target enters the system. To absorb the target, the system physically expands. It deploys structural solutions, investing in new machinery and rolling out upskilling modules. The operator node remains perfectly stable. Achieving a Clause 6.2 objective strictly requires a concrete systemic action plan. If current processes are operating at maximum capacity, the solution must be structural, involving capital investment or new training architectures. It cannot be behavioral. Clause 6.2 compliance is achieved by engineering the system's operational capacity, never through the extraction of human willpower. Deploying these systemic action plans across an entire enterprise relies entirely on the final requirement: communication. Auditors consistently find that companies confuse the act of distributing policy documents with actual communication. This visual tracks the difference.
Communication is complete when the nodes themselves permanently align into a unified state, rather than simply passing data through the chain. Effective QMS communication results in a synchronized comprehension of the objectives throughout the system. Operational staff must understand the specific intent and the exact mechanics driving those objectives, rather than just memorizing the final target numbers. This level of cognitive alignment ensures that when friction inevitably occurs on the factory floor, operators can react in perfect synchronization with the strategic goals. Tunification takes a static quality objective and transforms it from a piece of paper into a synchronized enterprise-wide operational behavior. The modern operational environment operates under extreme time compression. The era of static 5-year strategic quality plans is effectively over. Technological acceleration, particularly the rapid integration of artificial intelligence tools, demands high-frequency, sometimes monthly, updating of QMS objectives. This level of volatility brings us to Clause 6.3, Planning of Changes. A dynamic QMS must actively control its own evolution to survive. This structure models the concept. A rigid system breaks apart and instantly reconfigures into a wider, more robust shape without losing its underlying integrity. Clause 6.3 is the mechanism that prevents the system from collapsing during periods of rapid objective modification. Maintaining stability requires specific change management tools, and the QMS must apply different frameworks based entirely on the scale of the disruption. This decision tree maps the approach. The system separates responses into Path A for micro changes and Path B for macro changes. Path A handles daily disruptions, like material swaps. These require rapid response frameworks, like the 4M escalation plan. Path B handles macro-level structural adjustments, like corporate organizations. These require complex transformation architectures, like the Kurt-Lewin model. Applying this requires 3 phases: unfreezing current processes, changing to the new state, and refreezing into the optimized shape. Applying these specific architectural frameworks ensures the QMS maintains total operational integrity, even in the middle of massive corporate restructuring. An ISO-compliant system does not survive through mechanical adherence to initial targets. It survives through precise measurement, systemic capability enhancement, and rigidly controlled adaptability.